These are tiny electronic components composed of semiconductor material. This one is called a transistor. It's an amplifier that serves the same purpose as a triode vacuum tube. This one is a crystal rectifier or diode. It does the same job as a rectifier tube. Both of these devices utilize the same basic principles of operation. Since the diode is simple, we're going to use it as an example to show you some fundamental principles that apply to all transistors and diodes. Here's a circuit that will show that the tiny diode really is a rectifier which conducts current in one direction. The bulb is lighted now. If you reverse the voltage, it won't light because virtually no current can flow through the diode in that direction. Let's see how this crystal rectifier is constructed and what gives it this one-way characteristic. This crystal is made of a semiconductor material, silicon in this case. Germanium and other materials can also be used in the same way. Semiconductor simply means that the material may or may not be a good conductor. Since we are interested in the conduction of the crystal, let's review electrical conduction briefly. Here's a simple DC circuit. The current in the wire consists of negatively charged particles moving through the wire toward the positive battery terminal. These negative particles are called electrons. They are always present in the wire, but they move as an electric current only when voltage is applied. Let's look at this section of the crystal closely. It is one crystal, but to make it a rectifier, each half has been chemically treated or doped so that the two halves conduct electricity differently. In one half, the material is called N-type. In the other half, P-type. Remember, this crystal is one piece, not two pieces joined. Let's look at N-type material first. If the semiconductor material were absolutely pure, its atomic structure could furnish no free charged particles, such as electrons. With no free particles available to transport electric current, the semiconductor would be a non-conductor or insulator. The chemical treatment introduces a few foreign atoms, each of which contributes one free charged particle to the crystal. In this case, the charges are negative, so the particles are called electrons and the material N-type, N for negative. The free electrons constantly dart about at high speed, much faster than can be shown here. This motion will increase if the crystal is heated. It will slow down when the crystal cools. The rate of motion depends upon the temperature and is usually referred to as thermal agitation. This is important to the behavior of semiconductor material, but we're much more concerned with the reactions of the free electrons when external voltage is applied. Also, the atoms take no part in conducting current, so let's eliminate both the atoms and the thermal agitation. Let's assume that the whole crystal consists of N-type material. If we apply voltage, current flows. Both the crystal and the wires contain free electrons which carry the current through the entire circuit. Now let's examine the other half of the crystal, which is made up of P-type material. The pure semiconductor material has been chemically treated by adding a few atoms of another material to the crystal. One free positive particle has been supplied by each of these added foreign atoms. This material, so treated, is called P-type, P for positive. The free particles are called holes. These holes act just the same as free electrons when used as carriers of electric current, but are positively charged. These holes are also thermally agitated and are responsive to external voltage. If we apply voltage to P-type semiconductor material, current flows conducted through the crystal by the holes. As you see, the positive side repels the holes toward the negative side of the crystal. In the circuit, this direction is opposite to that which electrons would take. Holes and electrons are created in pairs at the positive terminal. the electrons move through the wire and the holes move into the semiconductor. The holes meet electrons from the wire at the negative terminal and they disappear in pairs. We thus have a continuous flow of current in the circuit since electrons are moving in the same direction in both wires. Let's see how the crystal acts as a rectifier. One half is N-type material containing free electrons. The other half is P-type containing free holes. We have a typical PN junction where the two types meet. Diode operation is predicated on the operation of this junction. When we apply voltage to the crystal, the electrons and holes move away from their respective voltage connections toward the junction because like polarities repel each other. The holes are repelled by the applied positive voltage on the P side, and the holes can easily cross the junction into the N-type material. Eventually, each hole meets an electron. When this occurs, the equal charges combine and cancel each other, neutralizing the energy that kept them in motion. Electrically, they simply disappear. Electrons cross the junction into the P-type material in the same manner where they also encounter and combine with holes. The particles disappearing in these combinations are immediately replaced by other electrons and holes entering the crystal. If the voltage is applied to the crystal, negative to N-type and positive to P-type, current flows. This voltage application is known as forward voltage or forward bias. When voltage application is reversed, the holes and electrons are attracted to the terminals and are drawn away from the junction. Charged particles now find it practically impossible to cross the junction, resulting in virtually no current flow. The crystal, in this state, becomes a non-conductor. This application of voltage, positive to N-type and negative to P-type, is called reverse voltage or reverse bias. Thus, the semiconductor crystal with a PN junction conducts current freely with forward bias, but is an effective block to current flow when reverse bias is applied. This ability to pass and block current in a semiconductor crystal utilizing the PN junction is used not only in diodes, but in transistors. Transistors, like diodes, also consist of one semiconductor crystal. If we remove the cover of a transistor, we find that the semiconductor crystal consists of 3 sections with 2 PN junctions between them. The crystal may be doped so the center section is N-type and the 2 N sections P-type. This is called a PNP transistor. The crystal will function the same if arranged like this. This is called an NPN transistor. The PN junctions in both cases function as rectifiers. The center section must be very thin, perhaps no more than 1/1000th of an inch thick. The N-type semiconductor material again contains free electrons. The P-type, free holes. Let's see how the transistor functions as an amplifier. If we apply reverse bias to the right-hand PN junction, this will attract the electrons and holes away from the junction so that no current flows. This circuit, connecting the right end to the center section, or collector to the base, is called the collector circuit. It is the amplifier's output circuit. Now let's put forward bias on the left-hand junction. That is, between the left side, termed the emitter, and the base. This is the emitter-base junction and is the amplifier's input circuit. This forward bias allows the electrons in the emitter to easily cross this first junction into the base. If the base were thicker, say 1/4 of an inch, the base emitter junction would operate as a forward biased rectifier or diode. With current flowing, only in the emitter circuit. No current would flow across the base collector junction due to its reverse bias. In this configuration, many of the electron and hole combinations take place far into the base material. Many of the electrons do not encounter holes at all until quite some distance past the emitter base junction. Actually, the base material is quite thin, and most of the electrons pass through it without meeting holes at all. Since the collector is negatively biased with a positive charge, the collector terminal further attracts them across the collector junction, and there is now collector current in spite of the reverse bias. There is practically no current through the base to ground because most of the emitter's electrons pass right through the base to the collector. The thin base contains such a small amount of p-type material that relatively few holes are available for combination. A few combinations do take place in the base and emitter, but this base current is so small that we can ignore it. The emitter current consists almost entirely of electrons which cross the junction into the base. These electrons cross the second junction into the collector and proceed on into the wire toward the positive battery terminal. The collector current is wholly composed of electrons from the emitter, and the collector current is determined by the voltage applied across the emitter base junction. The collector current is controlled by the emitter voltage. This collector or output current almost equals the current in the emitter circuit, since it is basically the same current. Obviously, we do not have current gain. However, a transistor is a good voltage amplifier. When we insert a large load in the collector circuit, we get an output voltage many times as large as the emitter or input voltage. This load has no effect on the collector current, since the size of this current is determined only by the voltage applied across the emitter base junction. The same current will flow regardless of the size of the load, as long as the collector has positive bias to attract the electrons driven into it from the emitter. Thus, we can insert a high resistance load in the output and get a large voltage drop across it. While the output current and input current are practically the same, the output voltage is much larger than the input voltage. Since power equals voltage times current, we have more power in the output circuit than in the input circuit. We have power gain or amplification. The transistor is an amplifier as long as the collector has reverse bias to attract the electrons. However, the voltage developed by the load is opposite to the collector bias voltage. Thus, the output voltage must always be smaller than the bias voltage. If the voltage drop were too large, it would be opposite to and would cancel the collector bias voltage, stopping the action of the transistor. The collector battery voltage and resistance of the load will determine the collector current. There would be no amplification since the emitter battery has lost control of the collector current. Let's amplify the audio frequency signal supplied by a microphone. The minute AC voltage output of the microphone is superimposed on the emitter bias voltage. With a loudspeaker as the load and a typical transistor, the output power might be 150 times as large as the input supplied by the microphone.